Hi, and welcome back. Now, we already know about all the consequences for TOPIT of heteroscedasticity and non-normality. You got inconsistent estimates, especially if there's a lot of censoring. Okay, so it may be important to test for these misspecifications. There's several ways to do this, and one way is to derive a test statistic under the null that there is no unobserved heterogeneity and see if that behaves according to the distribution you would expect if the null is true. Okay? Another way to do it is to estimate the model under weaker assumptions and then see if the parameters you get for that model adds up with the parameters that you get for your more restricted model. You can do, say, a parameter test where they test these two hypotheses against each other, just like we did with the Hausman test for the linear regression model for pan data with random effects and fixed effects. So anyway, so that's the overall the different approaches. I'm going to start with two tests for normality and homoscedasticity and normality. I'm not going to implement these in Python, but I want to talk about them just to get an idea, at least get an idea that these assumptions are testable, okay, and what those test statistics might look like. Okay? So just a brief overview, you can test for homoscedasticity using a Lagrange multiplier test or LM test against more general alternatives. Essentially, this looks at the scores of the the likelihood function, but I'm not going to spend so much time on that. But you can also do, say, you can even do like a likelihood ratio test where you estimate the model under a more general specification. For example, the right likelihood in the case where you have this homoscedastic errors. It may be a more complicated likelihood, but in principle, it's possible if you want to allow for this heteroscedasticity in a specified way. You do a likelihood ratio test between the two specifications. There's a lot of details in Woolrich, and I'm not going to spend so much time on this. I want to talk a little bit more about the test for normality. And specifically a conditional moment test by Newey, Tauschen, and White that's mentioned in chapter 13 on maximum likelihood. There's a section there on conditional moment tests. These are very powerful tests that we can use in many different contexts. And I just wanted to give you an example of that in the context of the TOPIT model. Okay, so it's going to be on the following slides. But you can also try to estimate the model under more general alternatives. For example, the Powell estimator or the central least absolute deviation estimator that does not assume normality, we can look at that after this conditional moment test. Okay, so that's three slides. So if you totally zone out and don't get it, at least there's an end after these 4 slides. Okay. So here is the Newey-Tauschen-White test statistic, okay? So basically, it's a quadratic sum of some moment restrictions here, and then weighted by some variance matrix, and then that if those moments are true, or those restrictions are true under the null, they're supposed to be that under the null, well, then this is going to be chi-square distributed with r degrees of freedom equal to the number of moment restrictions you are making. Okay, so here that's just a vector of ones. M is n by r vector of sample realizations of moment restrictions. I'm going to give you an example just in a second. And Q here is a weighting matrix. Okay, really the optimal weighting matrix here in this case would be the variance of those moment restrictions. And if you think about it this way, this is just a sum of restrictions that you normalized by those variances, and then under the null, those restrictions are going to be normally distributed. And if you normalize those with the variance, kind of, I know this is like not super precise, but if you take something that is normally distributed, divided by the standard error and square it, and that's kind of ballpark what is going on here, then you get a squared normal distributed variable. Okay, and now if there's only one of them, well, that's going to be chi-squared distributed with 1 degree of freedom. If there's 2 of them, say you have 2 restrictions, well, then there's going to be chi-squared distributed with 2 degrees of freedom, because you have the sum of 2 squared normally distributed variables. Okay, if you are of them, then it's going to be chi-square distributed with r degrees of freedom. Okay, that's why we often end up with this chi-square distribution. It's really, we try to take come with restrictions or a test statistic that's normally distributed, asymptotically normally distributed, normalize it by the variance, square it, and then add them up as many restrictions as we have, and then that's going to be chi-square distributed with the number of degrees of freedom as you would have in the number of degrees of freedom in the chi-square distribution equal to the number of restrictions that you have. Okay, yeah, this is the kind of stuff you have to sit down and with your probably like your feet in soap water and listen to some some music to really regret that, but you'll get there. Okay, let me give us some examples on basic what those moments might be. I'm gonna start simple because we are just forget about Tobit for a minute and let's just think about the linear regression model. Okay, so in the linear regression model, we would be able to derive the disturbances or the residuals from the model simply just saying, what is y star minus x beta? Okay, now assume we observe y star. Okay, and so that would be what you would have if you're just doing linear regression of y star and x beta. Now, if those are errors are normally distributed, well, we know, first of all, they're going to have mean 0, okay? So the first moment, not these two here, but the first moment, the conditional mean of u given x is going to be equal to 0, okay? We use that as an identifying assumption to back out what beta was, okay? Now, if it's normally distributed, well, with a homoscedasticity, we also would like to have basically that the conditional variance was equal to 0. That would be like u squared conditional on x being equal to 0. Okay, so that is there's no dependence between u with the squared residuals in x. Okay, so that would be things we could impose as moment restrictions. Actually, this could be a restriction we could impose here as well. Okay? But the first one we cannot use. We cannot use that to test because it's going to be satisfied always in the linear model. Okay, we always have this conditional mean independence assumption that the errors are uncorrelated with exponential variables. By construction is going to be equal to 0 if you've estimated the model with OLS. That's our identifying assumption. But you can test other assumptions, okay, on the residuals. You can test because you can back out the entire distribution of the residuals. So you can test if, for example, the third moment would be equal to 0, the third conditional moment. Okay, so you could test whether, and what is this measuring? It's called something called the skewness. We know that the normal distribution is a symmetric distribution. And so the skewness is going to be 0. So this normal distribution, it's like, it's symmetric around 0. Looks like this. It's not like going to the right or anything, or, the other way. I guess, in video, it's hard to know what is right or left, but you know what I mean. It's not a skewed distribution. And then that is what the skewness is measuring. Okay. So if that is 0, it's a symmetric distribution. And we want to impose that restriction. We want to test if that is actually true. Okay. Didn't appear so in all the, for example, the log normal distribution, when we simulate all those errors, they were not skewed they were not symmetric by any mean, with like, they were climbed up on one side, right? Okay, then we have basically, you could test other moments too. The fourth moment, that would be the ketosis, if you've heard about that. What does that kind of describe? Well, it says the ketosis, that's something about how fat are the tails. That gives something about the shape of that distribution. Is it very peaked like this, or is it more, or how the tail's looking? Okay, and so so that's also implied. Once you assume what the normal distribution is, and you assume that the variance mean is 0, the variance is constant, sigma squared, then you can calculate basically what the ketosis is. It's going to be 0. That's always the case for normal distribution. And you can also calculate what the ketosis is. Well, it has this formula here. It's going to be 3 to the times the standard deviation to the power of 4. Okay, so if you have like a standard normal distribution, the ketosis is always 3. Okay, and so what we can check, that is our moment restriction, is the expectation of the error equal to that moment. Okay. And so if we wanted to do, and here it's like implicit, the restriction is the expectation of u to the power of 3 equal to 0. Okay. Well, these are our restrictions. So if these restrictions do not hold, there should, if errors are normally distributed, well, then we can reject our hypothesis of normality, okay? Because these restrictions, they must hold, okay? Okay, so under these assumptions, then our basically for the ith observation, our restrictions would be these following. These are things that are supposed to be equal to 0 under the null. Okay, so this is what we have inside here. Just put those inside a bracket, and then you can calculate this test statistic. Well, we still need to know what Q is, okay? But Q can be calculated and derived basically as the moment restrictions, as the variance covariance matrix for these moment restrictions. Okay, and I'm not going to spend so much. This becomes a little bit hairy, but you can do it. Here's how it looks like for the conditional moment test under normality for the Tobit model. Okay, now they're a little bit different. We have exactly as we had before if this I is always equal to 1. Now, what does that mean? Well, that means that's an indicator for observations not being censored. You get exactly the same as you had before. You have, u to the power of 3 or u to the power of 3 minus 3 times the standard deviation. And these estimates here, well, we estimate those from the Tobit, because under the null we have consistent estimators of those. Okay, these guys here, this indicator here that appears over here in the other part that is due to the censored part of the distribution. Well, as you can see, they depend on the normality assumption. There's the inverse Mills ratio and a bunch of stuff I'm not going to go into details with. But the bottom line is you can see basically these conditional moment restrictions can be derived under the null that the normal distribution, that the errors were actually normally distributed. That is under the null of the Tobit model. Okay, then you get these expressions here, and these are things you can calculate. Okay, you first estimate beta and sigma using a Tobit model. You stick into all these expressions, and then you put this into your computer, and bang, you got your MI. And it's just a matter of summing all of calculating all this. Well, you still need to calculate the Q matrix, but that matrix we can calculate as well, the scaling matrix here. And V here, that could be basically the variance covariance matrix from the Tobit model that can you can estimate in either a different forms. So you can use the inverse of the Hessian or the inverse of the outer product of the scores, or you can calculate the robust variance covariance matrix, which is probably what is the best thing to do in this case anyway. But all these matrices here, they can be computed, and then you have your test statistic. Then the last step is just to check, is that chi-squared distributed with 1 degree or with 2 degrees of freedom? Now you don't have to impose all these restrictions. Well, you don't have to impose both of them, right? You can just have a single moment. If you want to test it, for example, is the Skewness Ketosis, is the Skewness implied by the Tobit model in accordance with our assumptions? Well, then you include only the first moment and make the test with 1 degree of freedom. Or you can do the other one where you look at the Ketosis. Is the tails as fat as we would expect? Well, then that's again a chi-squared test with 1 degree of freedom. But if you want to do both of them, well, then there is 2 degrees of freedom because there's 2 restrictions. Okay, essentially it's a sum of squared standard normally distributed variables of 2 of them. So we have 2 degrees of freedom. Okay, and yeah, so that's one way to go forward to test these assumptions. So I don't expect you to follow all the details of this, but I think it's really important to know that there exist these tests, and other people have implemented this in software, and you need to know what it is that you're really testing. Okay, but actually, it's a good exercise to try to see, could you use the simulation module we have in this Python code, simulate some data under the null and see, is this chi-squared test, is it, or this conditional moment test is that in fact chi-square distributed under the null, and you know, calculate it like many different times for many samples of the observations, and then you can show that it looks like a chi-square distribution. Then you can try to see, okay, what happens if for example, if I misspecify the model so that the errors are no longer normally distributed, does that Monte Carlo distribution look different? Well, maybe it does, right? Maybe it does no longer look like a chi-square distribution. So I think really this shows the power of programming. In many cases, you can verify that, you know, the theory holds and make yourself really understand what is going on inside, you know, Woolridge's textbook. Anyway, so the next we're going to talk about is estimation under weaker assumptions. And we're going to take a little break before we do this. Okay. So, you know, see you in the next video.